Man, we really missed DGAL. Okay, so this is a first latent heat example. This is taking calorimetry, but also introducing phase changes into it. And on a lovely day, we have 10 grams of ice with an initial temperature of negative 10 degrees Celsius. And it's placed into a hot cup of tea. There's 200 grams of water, the tea, and it's at 80 degrees Celsius, and it's at thermal equilibrium with the mug that it's sitting in. So that means that the mug is at 80 degrees Celsius as well. It's a very hot mug to touch. But the mass of the mug is 300 grams, and we happen to know the specific heat of the cup is 0.9 joules per gram Celsius. That's a pretty standard specific heat for something like a ceramic or clay. What we want to know is, if we put this ice in the tea, I don't know why you do that, but if we did, what is the final temperature of the tea? Could we work that out? So let's think about this, what's happening here. We have initially a cup. We have this hot tea inside it, so I'll make it red like it's lava or something crazy. And then we're taking ice and putting it in. So we know that this ice has to do a few things, right? We know the ice has to warm up. And then we have a pretty good feeling here that this ice is actually going to melt. Okay? We'll have to double check that because there is a possibility where the ice warms up, but it doesn't melt. So maybe the ice will melt here. Maybe we'll have to check that. And then in theory, because that energy is coming from somewhere, maybe this tea and the cup are going to cool down. So let's put all of this kind of into one here. First, let's try to figure out just how much energy it would take in order to, well, if let's just assume at this point that the ice is going to melt, okay? There is a way to kind of prove that. We'll see that at the end of here. But let's assume all this is going to happen. So if we wanted to warm the ice up, we need to use Q equals MC delta T, okay? So we know that this is the mass of the ice, mice, times the specific heat of ice. We'll have to look that value up. Then we know that there's going to be a delta T here. This delta T is the final temperature of the ice minus the initial. So we know that the initial is negative 10 degrees Celsius, but what's the final temperature of the ice cube? Well, we actually know that. We know that once the ice hits 0 degrees, it's not going to heat up anymore. It's going to melt, and it's going to become water. So once this ice becomes water, we're going to have the mass of the ice, because that is the mass of the water, right? It just melted, multiplied by the specific heat of water, which we know is 4.186. And then what's the initial temperature of this iced water? Well, it's 0. And then it's going to reach some final equilibrium temperature, right? Because it's cooling the tea down to something. When we add this to the mug, we've got the mass of the mug, we've got the specific heat of the mug, and then it's going to reach some equilibrium temperature, and it started at some initial temperature, which was 80 degrees Celsius. And then we have the tea itself. We've got the mass of the H2O, which was the tea, the specific heat of H2O, which is at 4.186, and then the delta T here will be the equivalent temperature at the end, or the equilibrium temperature at the end, minus the initial temperature of 80 degrees Celsius. And all of this is equal to 0 because we have a closed system in this problem. And the nice thing about this here is we know the mass of the ice. We can look up the specific heat of ice. That's a number. We know that mass again. It's what we had initially. We know this number. 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 We know everything, but we're just looking for this equivalent temperature. So there's nothing too crazy here of what's going on. Except, aren't we missing something? We're missing the entire reason we're doing this example problem separately. We've heated up our ice, and then we heated up that ice, which became water. How did it become water? It melted. There is a latent heat here. It's a latent heat of fusion, which for water, we know it is 333 joules per gram. So what we need to squeeze into here, and what everybody forgets in a problem like this, is this latent heat. And the way we define latent heat, it's just a mass multiplied by this latent heat. That will give us the energy required to melt this ice. And since this ice is melting here, this will be a negative quantity. This ice is leaching energy from the system. Wait a second. Okay, so this isn't going to be negative. What am I saying here? It's going to be positive. That ice is going to be heating up. It needs energy to do that. So this ml is going to be a positive value here. So we still know the mass of this ice here. And because it is melting here, it's going to be a positive value for that latent heat. If it was freezing, it'd be negative, excuse me. But it's a positive value there. So let's put in all of our numbers here and start working this out. This is the one thing about calorimetry problems, especially with latent heats. They become giant. There's 1, 2, 3, 4, 5 parts of this problem. So here we go. The mass of the ice is 10 grams. And I like to keep everything in terms of grams. So we've got 10 grams multiplied by the specific heat of ice. So our spec heat of ice here is somewhere around 2.04 kilojoules per kilogram. I like to just say joules per gram, so joules per gram Celsius. And then multiplied by, well, 0 minus negative 10. We'll just call that positive 10. Boom, there it is. And then the next part, so plus the mass of the ice, which, is now trying to melt. So it's 10 grams, and then multiplied by 333 joules per gram. And now we need to heat the ice up, or we need to heat the ice that have melted. So we're going to get our 10 grams again, multiplied by 4.186. And then here, TEQ minus 0 is just the equivalent, or the equilibrium temperature. And then we add the mass of the mug, which up in the problem we were given the mass of the mug is 300 grams. That's a 300. Maybe if I wrote that a little clearer, it'd be easy to see. The specific heat was 0.9, and then the equilibrium temperature minus 80. We're going to have to do some distributions in a second to hit both of those numbers. Ugh, that's annoying. And then plus the mass of the tea itself, which was 200 grams, multiplied by the spec heat of water, which is 4.186. And then there's the equilibrium temperature, TEQ, minus 80. We're going to have to do another distribution here, which equals 0. So, whew, that's just like a few numbers, right? Nothing too crazy. This is annoying, but at this point, we can just run through this. Okay, it's number time. So let's try to work this. 10 times 10 is 100. 100 times 2.04 is 204 joules, because these are all energies. Plus 10 times 333 is 3330. Plus 10 times 4.186 is just going to give me 41.86, but this is TEQ, because there's that variable there. And then this is where things become a little bit hectic. So I need to multiply 300 and 0.9 together. I get 270. But this is going to give me 270 TEQ. And it's going to give me 270 times negative 80, because I'm distributing this value throughout. So 270 times negative 80 is going to give me minus, because plusing a negative, 21,600. And then I need to do the same thing over here. I'm going to have 200 times 4.186, which is going to give me 837.2. So I'm going to have 837.2 times TEQ minus, because of that, negative 80. So then times negative 80. It's going to give me negative 66,976 equals 0. Huh. So this is a little big, but all the TEQ values, these are like terms, so we can just shove them all together. And then all the things that are just numbers here with the green lines through them, I can just plug all those together. I can just add all the numbers, add all the TEQs, I'll get two things, and this algebraically isn't that hard. So 204 plus 3330 minus 21600 minus 66976. Oh boy, I get negative 85,042 joules. And then all my TEQs are positive, so plus, and let's add all the TEQs up, 41.86 plus 270 plus 837.2 plus 1,149.6 TEQ equals 0. And at this point, this looks way easier to solve. This is actually something that I would have loved to see, 10 minutes ago. I'm going to add the 85,042 over to the other side. And then I'm going to divide by the 1149.6. So we see that TEQ equals 85,042 divided by 1149.6. And we get some number here. 85042 divided by 1149.6. We get a number here that is 73.98 degrees Celsius. And that's nice because our T, it cooled down a little bit. So our T has cooled down here. It went from 80 degrees Celsius to 73.98. We accounted for everything in it. We accounted for heating up the ice. We accounted for melting the ice. We accounted for heating up that little bit of very cold water. And then we cooled down the mug and we cooled down the very hot tea in there in an isolated system. And in doing that, with latent heat and calorimetry, we were able to figure out exactly what our equilibrium or our final temperature was for this closed and isolated system. A lot of numbers, not really the best thing in the world in terms of just analytical physics, but it's not a crazy idea. You're just kind of thinking through the problems, what's heating up, what's cooling down, and what's happening there. And it's important to remember, I had a slight misstep at one point. When we are melting ice or melting an object, this ml here is a positive value. We are adding heat into that substance, so that's a positive value there. Okay, so important thing to recognize. If you are trying to freeze water, that would be a negative because you're trying to take heat energy away from that liquid. But you are trying to, move to the right on the temperature energy graph, and that means you're going to have positive values there to heat it up. So with that, this little example problem is indeed finished. I hope you enjoyed that. It was a super long one, but it's not too bad. Until next time, adios. Take it easy.